Um, let me say a couple of words about the next homework. The first one, next time is, well, just kind of the truth table, right? So show this crazy statement up here, not A implies B, and not C, and not B or C implies A. Show that that's its tautology. So the way to go about that, I think, is look at the truth table. Number two, this is, so we're proving a couple of things as an exercise in proving, but also because some of these things we're going to use quite a bit. Here's some familiar properties of the absolute value. Everybody, I hope remember what the absolute value number is. If I ask you, what's the absolute value of 2? 2, right? What's the absolute value of -7? What did you do in your brain to do this? Well, you listened to what I said, and if I said a positive number, you just left it alone. And if I said a negative number, what did you do? You switched the sign, right? So if X was negative, you switched the sign to make it positive. So here's some familiar properties of absolute value that you should show. Show the absolute value of X times Y is the absolute value of X times the absolute value of Y. Show that the absolute value of X minus Y is equal to the absolute value of Y minus X. There are other properties like this. This is the most interesting one. Show that if you have a negative number and X is less than or equal to Y, then when you multiply that inequality by the negative number, it reverses it. So if X is less than or equal to Y, then ZX is greater than or equal to ZY, if Z happens to be negative. And finally, the triangle inequality. That is, the absolute value of X plus Y is less than or equal to the absolute value of X plus the absolute value of Y. You can use the standard definition of the absolute value. There's another definition of the absolute value that's equivalent to this. It might make the proof easier. So if you can think of this in terms of another function that you might have seen in calculus, might be able to make that easier. Number 3, suppose n is a integer and q is a rational number. That's what that means here. So in other words, n is an integer, positive or negative, counting number or 0. Show that the square of n is odd if and only if n is odd. So there's 2 things to show here, right? This is an if and only if. Show that if n squared is odd, then it follows that n must be odd. And show that if n is odd, it follows that n squared is odd. One of these is easier than the other, but neither one is too hard. This is an important one in number theory and code. Currently I have 2 B's there. Sorry about that. That's what B and C. Show that n is odd if and only if n squared minus 1 is divisible by 8. So if you ever have an odd number and you square it, subtract 1, it's always got to be a multiple of 8. And finally, this is also an important property here. Show that, remember, Q is a rational number. Show that a rational number square is actually turns out to be an integer if and only if that rational number happened to be an integer in the first place. Now, again, you've got 2 things to prove. If the square is an integer, prove that it's an integer. That's the hard. The easier one is if it's an integer, then the square is an integer. That one's easier to justify. Okay. Finally, for the following problem, you may freely use the Archimedean property of the real numbers R. The Archimedean property states that if you have, probably all heard of this before, or you might at least intuitively know this. If you have any real number, if I walk up to you on the street and give you a real number, there's a natural number that's bigger than it, right? You can find some natural number bigger than any real number. An equivalent way to state this is if you have any positive real number, there is a natural number n such that 1 over n is smaller than that positive real number, right? So give me something like, I don't know, 0.12, then if n is 10 or if n is 11, then that's less than that because 1 over 10 is 1/10. So you can use either of these freely. This is a twist on something that I mentioned the other day, but this is kind of a warm-up. You're going to need this for this, or you might anyway. Show that if alpha and beta are real numbers and the difference is bigger than the natural number n, then you can squeeze at least 10 distinct integers between alpha and beta. So if beta minus alpha is bigger than 7, then between alpha and beta, I can fit at least 7 integers. Right. That's the warm up. The follow up is show that if alpha and beta are any two real numbers, no matter how close together, I can find a rational number between them. How many of you have heard of this before? If you have any two real numbers, you can squeeze a rational number between them. Well, you're going to prove that. And this is an important part of the rationals and the reals. Is in between any two real numbers, you can squeeze a rational. You might need part A to help you out there. Okay, any questions on that? All right. So what I want to do today is kind of start getting down and dirty with some examples of proofs. And I'm going to start off with one that you may, I hope, or may not have seen in calculus. So I'm going to start off now. Before I do this, so example, yeah, show that if f of x is a function differentiable a, then f of x is continuous. You'll all probably remember this, I hope. Theorem of calculus, if you're continuous, I'm sorry, if you're differentiable at points, continuous at points. So I guess probably one of the things I want to make sure we're all on the same page. What am I allowed to use here? What are my definitions? Does anybody remember what it means to be differentiable at A? Well, yes. Yeah. Right. More formally, f of x is differentiable at A. Yeah. If that limit exists, right? There was another way that you might have done it. F of x plus h minus f of x over h, as h goes to 0. This is going to be more convenient problem. And remember, my notation is f prime of a. That's what this thing is, right? And this is what it means to be differentiable. If this limit exists. Agreed? If I remember what it means to be continuous at a. Yeah.
The limit as x, which is a the right equals of f of x equals f of a, and the limit as it is
That's right. I'm going to write that a little bit more compacted, which you said is correct. The limit as x goes to a of f of x equals f of a. Right. So this thing says several things. It says that the limit as x goes to a of the function exists, and it's actually equal to the value of the function. Right. These are, I mean, let's not prove anything unless we know what we're talking about, right? So let's make sure that we're all agreed on what it means to be differentiable and continuous. And we will also I'll let us use any limit laws from calculus, right? Okay, so let's prove this. What does this ask me to do? If a function is differentiable, so differentiable implies continuous. That's what we're trying to do. So a good way to do this kind of proof, I'm going to call this a direct proof, is just to get on your boat and ride. What you have to do is assume that the function is differentiable and go through a logical sequence of steps to show that it's continuous. So what do we want to do? We know the function's differentiable. We want to show that this works. This is my tool, this is my hammer, and this is what I want to build with my hammer, right? So limit x goes to a, f of x minus f of a. Now, when I get finished, you probably realize this is, by the way, what do you kind of hope that this turns out to be? If it zero, right? I hope this turns out to be zero, right? So notice a slight cosmetic change to that. Let's see what we got here. What's the tool that I'm working with? I know the function's differentiable, right? And notice the similarity here. F of x minus f of a. Any ideas what I could do? Right, but you know, you can't just divide by itself. I mean, that's a great recipe. But now these two are no longer the same. Oh dear, how can I fix it? Doesn't have to sleep. This limit is equal to this limit. Everybody agree? The cool thing about limits is, remind me what it means. Limit is x goes to a. What does that mean? Not even formally. It means x is getting very, very close to a, but it's never equal to a, right? And so that's why we can get away with that, because x minus a in orange, in theory, it could be zero, but it can't, because x and a are never exactly the same. Right? Now that I've done this, what can I do now? What's one limit law that I can do? The limit of a product of two things is the product of the limits, right? Well, the lawyers are going to make me be careful about that. I'm going to write my next step. Boy, I'd really like to write this. Can anybody recall from the old days of calculus? So what did I do? I took this big blob limit and I split it up into two smaller limits. Under what conditions can I do this? You need both of these limits to exist, right? If I recall. Oh, I know how. I know why this one exists, right? Because this one's a polynomial. I gotta just plug in. Why does this one exist? Because we said so, right? Remember, the function's differentiable. Because of the fact the function's differentiable at a, this limit exists. Everybody agree with that? So this is f prime of a times the limit as x goes to 0 of x minus a. What's this limit? That is big fat 0. So let's collect, yes. Because this is a polynomial. So all you have to do to evaluate the limits plug in. Everybody okay? Now let's collect our thoughts. Where were we? So what we've shown is we now have that limit right there. Let me be formally over careful. What have I done? To both sides of this equation, I just added this limit as x goes to a. Of f of a. By the way, this is a bit of colorful silliness. Can somebody tell me why? What happens to f of a as x gets closer and closer to a? It's always f of a, because this is a freaking number, right? I mean, it's just f of a. This might as well be 2 or 7 or something like this. So I'm just being super careful here. I have this is just a number, this is just a number. And in fact, the number has to be f of a. And what happens in here? These cancel. So I get the limit as x goes to a of f of x is f of a. So f of x is continuous at a. Okay. Any questions on that? So what we've shown is a function that is differentiable at a point A is continuous at A. What did we do? We started with the tool of being differentiable. We knew what that meant. And we used that to show that function also must be continuous. Let me recall from last time, proposition 141. We're going to talk about this more extensively later. Every non-empty subset of the natural numbers non-empty is very important descriptor here. Natural numbers 1, 2, forever has a, anybody remember? Smallest possible. Smallest. Okay. Good. We will use this proposition freely here. Let me give you a definition, a couple of definitions of facts to kind of get things rolling. Definition 142. Let's see, here my playground is the integers. Okay, so I'm gonna make some statements about the integers. Number one, we say A divides B. In the integer. And sometimes we'll write A. Sometimes you see this notation, which means A divides B. So that means B of yeah, A divides B. By the way, anybody know what the definition is? What an appropriate definition would be? So let me ask you this, in the integers, does 2 divide 6? Yeah, 2 divide 6. How about does 2 divide 7? Okay, so what's the difference? Yes.
There exists an integer C such that
Yeah.
it multiplied.
So, right, we say that A divides B, and so you're right, if there exists A in the integers such that B equals A. Right, so for example, 2 divides 6, because 2 times 3 is 6, but 2 does not divide 7, because if that's a 7 and that's a 2, then K is not an integer, right? So it just means it's a fraction B over A. We say the integer P in C is prime if, anybody know what the definition of prime is?
It's 2 fractions.
That is equivalent. In some mathematical structures, it can be different. P is not plus or minus 1, and P divides the product of 2 integers and implies P divides A or P divides B. So what it means to be prime is, forget about being plus or minus 1. If it divides the product of 2 things, it has to divide one of the 2. How many of you heard this definition for prime? We say the integer, I want to call this a different notation. You say the integer x is irreducible if x is not equal to plus or minus 1 and x equals AB implies A or B is plus or minus. Oh, by the way, here, yes, AB is. Okay, so let's look at the difference here. To be prime or irreducible, it means you can't be plus or minus 1. But prime means if you divide the product of 2 things, you have to divide one of the 2 things of the product, no matter how you put this product together. Right? Notice 2 is a prime number, right? Because if you have the product of 2 things being even, one of them has to be even. Everybody agree with that? So that means 2 has to divide one of them. To be irreducible, it means if you ever break it down, one of the pieces you broke it down into has to be a 1 or minus. Right? 2 also satisfies this because factor 2, there's only one way to factor 2, 2 times 1, or negative 2 times negative 1. But in either case, you get a plus or minus 1 factors. Okay. A couple of things here. How many of you have seen this definition referred to as prime? Anybody ever seen this referred to as prime? That is correct for integers, but it's only because you get lucky. In fact, there are mathematical structures where this is generally a stronger condition than this. But there's also another kind of subtle difference. These two, like I said, 2 and 3 are almost the same. These are almost the same for the integers. There's one strange difference. Can anybody give me an example of prime integer that is not irreducible? Note 0 is prime, but not irreducible. Ooh, that sounds like something we should prove. Can anybody tell me why it's not irreducible? Irreducible means if you can ever factor it, one of the factors has to be plus or minus 1. Can anybody factor? See, yes. Okay. 0 is 0 times but neither factor is plus or minus. Okay, that almost fits like that cheap, right? So 0 is not irreducible. Zero is, however, prime. But wait a minute, there's something that bothers me here. I don't know about you all, but I'm used to thinking that 0 can't possibly divide anything, can it? Or can it? I'm gonna prove to you that if 0 divides AB, then 0 either has to divide A, or 0 has to divide A. Suppose 0 divides AB, where your A can be. Okay, tell me what that means. What does it mean for 0 to divide AB? Let's read the definition. There's a K such that B is 0 times K. Was AB 0 times K. Everybody agree with that? That's what it means for 0 to divide AB. What's 0 times K? Yeah, I don't care what K is, this is 0, right? Now, what do you know about products of 2 integers being 0? What must be true? If I tell you, ooh, I've got this mystery for you, I have 2 integers, A and B, and I'm not gonna tell you what they are, but if I multiply them, I get 0. What can you conclude? One of them, or both, have to be 0. Do I agree with that? Suppose A equals 0. In the first case, we'll suppose A is 0. Well, notice 0 equals, let me write this up automatically. Right. So 0 times A. Right? Because this is exactly what it means. Since A is 0, 0 is 0 times 1, so 0 divides A. And there you go. And case 2 is essentially the same. If B equals 0, then B equals 0, 0 times 1, so 0 divides B. So one of two things happens. Uh, 0 divides A or 0 divides B. And so 0. Okay, any questions on that? By the way, let me ask you one more question. It might seem kind of silly to you that in parts 2 and 3 of my definition, I toss out the possibility of plus or minus 1. Can anybody tell me what is unique about plus or minus 1 in the integers? This one might be a little hard to discern. Yeah, what do you think?
I'm not sure about it.
Oh, actually, that's actually a pretty good observation there, right? I mean, it's the only one that only seems to have one factor, right? That essentially kind of boils down to it here. Here's kind of another way to look at that. What is the reciprocal of 1? 1 itself. What is the reciprocal of -1? -1, right? Plus and minus 1 are the only integers whose reciprocals are still integers. This is not true for any other integer, right? 1/2 or 2, 3, 4, their reciprocals are not integers, right? And that's what makes them a little bit, we'll probably talk about this a little bit more later in class, but that's the thing that kind of makes them unique in a certain sense. Okay, let me prove a theorem. I'll give it to you first and I'll prove it for it. Let A, B, C be integers. The first one I want to talk about is transitivity. If A divides B and B divides C. By the way, anybody want to guess what the punchline is here? Suppose I know that A divides B, and then in turn B divides C. What do you suppose I might want to put this? Then A divides C. We should probably prove that. And 2, if A divides C and B divides C, then actually you can include a number. Oh, I'm sorry. That's not what I'm right. Boy, I could look at this. Scratch this whole thing. Freaked out. If A divides B and A divides C, then A divides B plus C. There we go. That's what I want. So if you have the same number dividing both B and C, then that number divides their sum. Okay, so let's go to careful proof of both of these. Let's do working first. Okay, we have A divides B and then B divides C. What we need to show is that A divides C. First step, this is kind of where we're starting off. So let's write down what this means. What does it mean for A to divide B? Okay. And the same sort of thing here, right? There exists K, M integers such that B equals AK and C equals MB. Everybody agree with that? B is a multiple of A, that's A divided B, and C is a multiple of B. What do I want to get? Where am I going? Well, I'm trying to go here. C is a multiple of A. And yeah, just how you can do that. I mean, what do I have? I have C is a multiple of B, but that's not good enough. I want it to be a multiple of A.
Substitute.
Fine. Reversing the order. Right? M is a multiple, I'm sorry, B is a multiple of A. Now, what do I know about M and K?
Sure.
They're integers. So what do I know about M times K? Also an integer. So, being careful here, since MK is an integer, and C equals MK A, we have the A divided C. And we've successfully proven that. Everybody understand the logic? See how we got that machine going? Question? Okay, how about the other one? I have A divides B and A divides C. I want to show that A divides B plus C. 2. Again, let's just write down what that means. So there exists K, M in the integers. I'll just use the same notation such that B and C. So what do I have? Oh, yeah. So what did I do wrong? Because I tried to copy too much. Thank you. Remember, my condition now is not that B divides C, it's A divides C. There we go. Much better. Now, what I'm trying to do is I'm trying to get A divides B plus C. So equivalently, I need B plus C to be a multiple of A, right? Well, let's just see what B plus C is. That is AK plus AM for MA, but what can I do here? I back to this out, right? K and M are integers, so what's the status of K plus M? Also an integer. Since K plus M is an integer and B plus C is A K plus M, then A 5 B plus C. Okay, any questions? Okay, so here's another thing, we're gonna use this to prove a lot of things, and you can use it for a ton of things. This is an extremely important important property of the integers. It's what makes the integers very sexy and useful. And it's the fact that it has the Euclidean algorithm theorem. This is Euclidean algorithm. How many of you have heard of the Euclidean algorithm? One of you has.
This is the one showing Grady's common factors.
Oh, it's right, I don't, let's see. Not quite. How many of you know how to do this problem? Right, I mean, both in there. Let me do it. Let me show off my math skills. Right? That goes in what, 9 times? And that leaves me, what was the 7? Bring down the 4. What's wrong with my answer?
It's 296.
Anybody want to complain about the remainder? Remainder's too big, right? I mean, if I was in grade school, I'd get my knuckles wrapped for that, right? Why? Because what's wrong with my remainder? Okay, how would I know that my remainder is small enough? Right, when I do this problem, oh, oops, this shouldn't be a 5, actually. My remainder is too big. This should have been a 6 down here, and it should have been remainder 8. What remainders, if I divide by 11, what remainders would be acceptable? Anything, a remainder that is not negative, but less than 11. So 0 through 10. Remainder 0 means 11 divides perfectly, and otherwise I'll get those 10 other possibilities, right? If you know that, that's the Euclidean algorithm, essentially. You can divide by something and get a remainder less than. Let me state it formally. Let n and m be integers. Here, m not 0. Then n can be written as q times m plus r for some integers q and r. Integers with the absolute value of n. In my formulation of the Euclidean algorithm, I even allow division by negative integers, just not 0, right? Let's look at the Euclidean algorithm back to this problem here. What do we do in this example? Well, what we did is we divided 3264 by 11 with quotient that's usually why this written as cube for quotient of what was it? Turned out to be 296. and remainder A. And what this means is my original number, whatever it was, 3264, if I did my division right, should be the quotient times n, or times m, which in this case is 11, plus remainder A. Okay. Okay. Any questions?
Um.
Now, just work. Anybody know how to prove this? This is actually kind of fun. I want to consider the following set. Put in and in the integers within not zero. And in fact, the proof basically works off the mistake that I made in my division there. Remember how I divided by not enough and I had a remainder that's too big? That's essentially what we're gonna do. Consider all integers of the form so I'm not divided n, so it should be n remember, n and m are fixed, right? So for example, this will be, let me tell you some of the things that will be in this. N will be in there because you could take q to be 0. N minus n is in there. N minus 2m, n minus 3m, and so forth and so on, right? Everybody agree with that? Also n plus n, because you could take q to be negative, right? Everybody agree with it? Would everybody agree that this is a subset of the integers? Every one of these things is an integer. Big set, it's very big, right? Because n and m are just numbers, but I'm allowing this to vary through all integers, right? So I get some subset. Now, consider the natural numbers. You can see, well, subset of non-negative elements of the set. Everybody. So in other words, this has infinitely many elements in it. All the ones that are negative, throw them out. Right. So S, I might write this as set of things n minus qn intersected with n0. By the way, when I write n0 here, that means the natural numbers with 0 thrown in. So in other words, instead of starting to count at 1 here and n0, you start to count at 0. This is a subset of n0. Right, okay? What's true about any subset of the natural numbers, or even the natural number being 0? It's got a smallest element. S has the smallest element. We'll call it R. since R is in the set. That's- There is a Q in Z such that R is Q M. I'm sorry, N minus Q. Because R lives in the set. And everything that lives in the set can be written as N minus QM, some Q, right? Now rearrange this a little bit. Sorry. Which is exactly on it. The last thing we need to do, what do we need to do to finish this off? We need to show that R is between 0 and the absolute value of M, right? But if it's not, if it's bigger than the absolute value of M, just subtract another M off of it, get smaller here, and that contradicts the fact this is minimum. I'll let you think about this and we'll go over that in detail next. But R must be think about that, and I'll make sure that that's on solid ground next time. Any questions? All right, let me remind you, the math club today, I'm actually going to draw out the cubic formula and get some really cool consequences. So if you're in the mood for math and pizza at 5 o'clock, please be there. I'll just be in 1 or 2.